Once upon a time, everything was a dust cloud. Isn't that the beginning sentence of many stories? We hear it so often that it seems somewhat emptied. However, this sentence actually points to the beginning of everything. It signifies the first step in all the changes our planet has undergone over billions of years. From the birth pangs of our planet, to all the struggles it endured to reach its current state, to all the existences and extinctions, explosions, warmings, dogmas, ultimately leading to the miracle called life. Despite our ruthless exploitation of its resources, our home, which harbors incredible beauty in every corner, became our home. How did our home become our home? The only place we know of, and most likely the only place where life can exist for a very long time. Could we not start our cosmic journey from a better place? Let's explore the universe together. Let's start this exploration right here, from the pale blue dot. The biggest problem is this. After billions of years of volcanic eruptions, ever-changing epochs that overturned all geological formations, landslides, storms, and continental shifts, finding traces of Earth's birth had become almost an impossible task. When you look at the rock formations on Earth, they are relatively recent formations. They don't tell us anything about how Earth was formed. We needed a sample of pure, untouched material that constituted Earth first. And unfortunately, we couldn't find it here, on Earth. We needed something not from this world. We needed a rock piece isolated from all the natural phenomena I mentioned earlier. We could only find such a rock piece in the depths of space. We needed to look to the stars because when we say, once upon a time, everything was a dust cloud, what we mean is this. 4.5 billion years ago, a cloud of dust and gas orbited the sun's orbit. As this cloud of dust and gas, spanning thousands of light years, cooled down, it formed tiny solid mineral particles. In short, these particles, naturally, began to collide with each other, stick together, and eventually form planets. Too short, right? I know we need evidence for this. How can dust particles come together and form planets? How is that possible? Theoretical scientists understood this. It was possible through static electric charge. However, we would learn about this formation firsthand only 17 years ago, in 2003, thanks to astronaut Donald Pettit, who conducted experiments out of boredom aboard the International Space Station. Donald Pettit, who wanted to see how different materials react under zero gravity, finally puts some salt into a plastic bag and shakes it. Do you know what the salt particles do? They start sticking to each other one by one due to static electric charge and eventually form a mass. Just like the dust particles around the sun, they come together, forming first a pebble, then large rock chunks, and finally, these are the initial movements that initiate the formation of Earth. Over millions of years, these rock pieces, like the dust particles, began to add up to each other and grow larger. What happens as they grow? Gravitational force. As the mass grows, it starts attracting smaller pieces around it due to the curvature of space-time, and in a chain reaction, it grows even larger. It's a formation similar to the game Agar.io, and one of these formations is Earth. As it grew on Earth, gravitational force increased even more. As gravity increased, it grew faster. As it grew, it began to attract even larger masses to itself, and an incredible meteor shower began. For 30 million years, an endless meteor shower continued. Billions of large rock pieces kept hitting Earth, and at the end of these 30 million years, the Earth had reached approximately its current size. But here we are talking about a planet formed by rocks stuck together. So, a structure very different from today's Earth emerged back then. Because when we look at the Earth today, there's a massive core made of iron and nickel alloy at its center. Above that, there's a layer containing extremely hot magma, which we call the mantle. And on top of that, there's a thin layer we call the crust. So, we have the core, mantle, and crust. How did these layers form, you may wonder? Well, here's the explanation. After the Earth formed, the rocks that constituted the Earth started to melt due to very high temperatures and eventually turned into a giant ball of fire. The reason for Earth heating up to such an extent, according to scientists, was the reaction caused by the billions of radioactive rocks that collided with the Earth. So, this accumulation of radioactivity, over 30 million years, had turned the Earth into a fireball. At this point, the heavy elements like iron and nickel in the planet, which had almost turned into a liquid form, began to sink towards the center due to the gravitational center. Meanwhile, the upper layer, with temperatures reaching 2,000 degrees, started to solidify due to the tremendously low temperatures of space, and thus, a solid layer began to form around the Earth. However, the Earth was still far from being habitable. The atmosphere was filled with methane and carbon dioxide. There was no water, and consequently, no oxygen. And more troubles were yet to come. Along with the Earth, countless planets of various sizes were completing their formation in the system. And at some point, a planet almost the size of Mars collided with our planet at great speed. Fortunately, we can say it scraped instead of hitting directly. Otherwise, we wouldn't be talking about the Earth. We wouldn't exist either. But it was a tremendous collision beyond comprehension. And it spread the newly formed continents, rock fragments, and the solid upper layer into pieces, scattering them across the Earth's surface and creating a new dust cloud in orbit around the Earth. Around the Sun, there's a cloud of dust similar to the one that formed the Earth. So, do you know what comes out of this cloud? Our Earth's satellite, the Moon. In fact, the planet that collided with our Earth is given the name of the Greek moon goddess Selene's mother, the planet Theia. So, how do we know about this collision? From a rock brought back from the Moon to Earth by the Apollo 16 mission in 1972. By the way, the lifeless object on this rock still exists. When this rock is examined, a very strange thing will be discovered. There was very little iron in the rocks on the Moon, unlike any similar stone on Earth or any meteorites. The only explanation could be that due to the iron accumulated in the Earth's core, very little iron remained in the surface crust, and hence, the amount of iron in the dust cloud spread from the Earth's crust due to the mentioned collision was also very, very low, and the Moon was formed from this cloud. The fact that there is much less iron in the core of the Moon also supports this theory. The Moon is actually a part of the Earth. So, when you gaze at the Moon in the evenings, you may feel it differently now. So how do we know the dates? Our Earth is about 4.5 billion years old, and the Sun is 4.6 billion years old. This rock is 3 billion years old. How do we calculate? Because until science figured this out, it took a very long time. It was thought that the Earth was about 5,000 years old on average. This conclusion was reached by calculating the ages and dates of the kings mentioned in the Bible. Even a specific date was given. It was known that the Earth was formed on October 23, 4004 BC. This problem would be solved by physicist Ernest Rutherford in 1897. While working on radioactivity, he would say that you can also find the date of rocks by measuring radioactive decay. We can technically explain this as follows. There are many radioactive elements in the universe. Radioactive atoms are structurally unstable. Over time, radioactive parent atoms are found to decay into smaller, stable daughter atoms. When a molten rock cools and forms what we call volcanic rock, it also traps radioactive atoms within it. These atoms are found within the rock at a known constant rate. Scientists can determine the time elapsed since the formation of the rock by comparing the amount of parent atoms with the amount of daughter atoms. And thus, through the study of a meteorite examined by Claire in 1956, we would learn that our Earth is approximately 4.5 billion years old. With measurements becoming increasingly precise over time, the closest estimate is that our Earth is exactly 4.567 billion years old. Of course, there were many more stages to go through for it to reach its current state. Yes, we know that a crust formed in the first few 100 million years. But how and when did the current continents form? More importantly, where did the oceans, seas, and water come from, and how were they formed? And most importantly, where and how did the miracle of life begin? As you can see, there's still much to discuss to fully understand the Earth's formation. But even what we've discussed so far should give us an idea of what our pale blue dot, our only home, has endured to become our home, so to speak. More importantly, in later videos, we'll understand better that we are a part of the vast universe, and it's a part of us. We cannot separate ourselves from it, and when we say we're a speck of dust in this universe, it's not wrong. Because as we said before, everything was once a game of dust clouds. And until we meet again, as always, thank you for being here. With love.